Hello. Finally, we're going to calculate the higher cutoff frequency for this common emitter amplifier, and that is FH. Now, in order to do that, I'm going to draw the high frequency equivalent circuit, just because it's going to allow us to see things more clearly. So let me go higher cutoff frequency. FH. And again, I'm gonna just redraw the circuit, the high frequency equivalent. So this is VS, there is RS in series. Just to make things a little bit more compact, I'm going to lump R1 in parallel with R2 into a single resistance. And then this is fed into the input of, or the base of my transistor. My base is connected to the emitter resistor RE1. My collector is also connected to ground via a collector resistor. And then my output is taken here, and I'm going to go ahead and, since we've added a large load resistor, I'm going to go ahead and include it here. I may as well just connect both of those in parallel, so let me do that, maybe more clear. So I'll have my RC going to ground, as well as my load resistor going to ground, and then here will be my output, V out. I have replaced all my bypass and coupling capacitors with short circuits, because now we're considering the high frequency region. And the other thing I need to include now are the capacitances that are going to affect the high frequency response. And those are going to be any internal capacitances of the transistor, as well as load capacitances, parasitic capacitances, etc. There are two internal capacitances. One of them is CVE, and another one is CVC. Or if you look at the datasheet, they will appear as input capacitance IBO and output capacitance OBO. That's what I've labeled them up there. And they're also sometimes referred to as CMU and CPI. CPI will be the one connected to the emitter, and CMU will be the one connected to the collector. And now I'm going to note that my CVC capacitor is connected between input and output, and so this is actually a feedback capacitor. And it's going to suffer from the Miller effect we have talked about, meaning any capacitor that is connected in the feedback path of an amplifier, meaning between input and output, it's going to appear as if there were two shunt capacitances, one at the input, one at the output. The one at the input will be equal to the actual capacitance in the feedback times the gain of the circuit. The one at the output is approximately equal to the feedback capacitance. So I'm going to do that change here. I'm going to replace that CVC capacitor with two shunt capacitances. One here, which I will call C Miller input, and one at the output, which I will call C Miller output. And with that, I'm gonna delete CVC. Because I've already replaced it with those two equivalent capacitances. Now for my CVE, it's really not directly connected to ground since I have the emitter resistor RE1. However, to simplify my calculations, I'm going to go ahead and assume it's connected to ground. if you do the calculations, you'll see that there's going to be not much of a difference in your result. But if you want it to be proper, you will need to analyze the circuit with that connection to the emitter instead. Myself, I'm just going to make the approximation that this is connected to ground, and therefore it's going to be in parallel with the Miller input capacitance, and so I'm going to consider my overall input capacitance to be equal to the sum of the two parallel capacitors, C Miller input plus CBE. So I'm just going to eliminate this and say, oops, plus CBE. And my output capacitance will be C Miller output. I did not consider any load capacitances, but if I had any load capacitance, I will just be adding it to CMO, to the output Miller capacitance. All right, so let's go ahead with the calculations. We have an input capacitance and output capacitance, and so two contributions to our high cutoff frequency. I'm going to refer to the one due to the input capacitor as the input high cutoff frequency. Value is going to be equal to 1 divided by 2 pi RC, where C will be my input capacitance. Just going to refer to as C input. We'll calculate it separately. And this will be the Thevenin resistance connected to that input capacitance. So C in this case is C Miller input plus CBE, and R Thevenin input is going to be whatever is connected to the capacitance, which will be RS. Again, we're going to short through VS, and so that will be RS to ground in parallel with R1, in parallel with R2, in parallel with little re plus RE1. So RS parallel R1, R2, in parallel with beta times little re plus RE1. I'm going to calculate that value separately. So RS will be 1 kilo ohm in parallel with 220K, parallel with 20K, in parallel with 100 times little r is 50, RE1 is 150, so that's 200. And that's going to be equal to around 900 ohms. Notice that it's going to be dominated by the 1K resistor, the source resistance, since it's the smallest. I can also calculate my input capacitance separately. My Miller input capacitance is going to be equal to my CBC capacitance times 1 minus the gain being negative 100 plus CBE. And so in this case, it's going to be my CBC, which was 4 picofarads, times 101 plus CBE, which is 8 picofarads. And that's approximately 412 picofarads. And now I can enter those values into my equation here. 1 over 2 pi 900 times 412 pico. And that's approximately 430 kilohertz. And finally, my high cutoff frequency due to the output capacitance, FHO, could be similar expression, 1 over 2 pi RC. In this case, C will be the output capacitance, and this will be the Thevenin resistance seen across that output capacitance. C out, in this case, is just going to be CMO, the Miller output capacitance, which is going to be CBC times 1 minus 1 over A. which is approximately equal to 1. So this is approximately equal to CBC, which is 4 picofarads. And the Thevenin resistance connected to the output is going to be RC in parallel with little r, the output resistance of the amplifier, in parallel with the load resistor in this case. So RC was 20K in parallel with 200K in parallel with 100 meg. We can see that RC is going to dominate that parallel combination. So that's approximately equal to 20 kilo ohms. So 1/2 pi 20K times 4 picofarads yields 2.48 megahertz. Approximately. All right, and now, just like we did before, we are going to use the dominant pole approach, and so we're going to approximate the high cutoff frequency as the minimum of FHI FHO, which in this case is just FHI, which is 430 kilohertz. And that's it. That completes our analysis here. I'm going to write here higher cutoff frequency. FH equals 430 kilohertz. And I'm going to highlight the results of, quiescent current, mid-band gain, input resistance, output resistance, as well as low and high cutoff frequencies for this common emitter amplifier. Before we go, a few things to note. Note that the dominant high cutoff frequency in this case is the one due to the Miller input capacitance. That's the one that has a highest effect on the high cutoff frequency. It's the largest. You can see it's around 400 picofarads because it is 4 picofarads multiplied times the gain of the circuit, which is 100. And that's typically going to be the case for a common emitter amplifier and for any amplifier that has a feedback capacitance and a high gain. The Miller effect is going to make that capacitance a lot higher than most of the other capacitances in the circuit, so it's going to dominate the frequency response and limit the bandwidth of the amplifier. Thank you.